In this lecture, we will discuss the relative strengths of acids and bases and the autoionization of water. In the last lecture, we introduced the fundamental concepts of acids, bases, and conjugate pairs. The information in this lecture will primarily focus on the relative strengths of acids and bases. We will also, in this lecture, develop a scale for measuring how strong an acid or base is relative to another. And lastly, we will see how to calculate the concentration of hydronium ion and hydroxide ion in water solution. The strength of an acid is a measure of how readily the acid donates a proton to a base. The more readily an acid donates a proton, the stronger it is considered to be. There are 7 common strong acids that you need to remember: hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, chloric acid, HClO3, perchloric acid, HClO4, nitric acid, HNO3, and the first proton on sulfuric acid, H2SO4. These are all considered to be strong acids because they will completely dissociate in water, donating all of their protons. For example, when nitric acid, HNO3, reacts with water, it completely dissociates to form hydronium ion and nitrate ion. After reacting, there is no nitric acid left in water solution. All of it has become nitrate ion and hydronium ion. The strength of a base is a measure of how readily the base accepts a proton from an acid. The more readily a base accepts a proton, the stronger it is considered to be. There are 8 common strong bases that you need to remember in aqueous solution. First, notice that all of these are hydroxide compounds. The first 5 are group 1 hydroxides: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. The last 3 are group 2 hydroxides: calcium hydroxide, strontium hydroxide, and barium hydroxide. These are considered to be strong bases because they will completely dissociate in water, donating all of their hydroxide ions. For example, potassium hydroxide, KOH, reacting with water, completely reacts to form potassium ions and hydroxide ions in solution. No potassium hydroxide remains in water solution. All of it dissociates to form potassium ion and hydroxide ion. Conversely, a weak acid is any acid that does not completely donate all of its protons. Most acids in water solution are weak acids. A weak acid will react with a base to donate protons, but only partially. This results in an equilibrium. We give the equilibrium constant for a weak acid reaction a special symbol, Ka. This stands for the acid dissociation constant. An example is acetic acid, which is a weak organic acid, CH3COOH. When it reacts with water, it forms an equilibrium and results in acetate ions and hydronium ions. In this case, a majority of the acid stays in the protonated form, and only a fraction of it dissociates into acetate ions and hydronium ions. As with other equilibria, the smaller the value of Ka, the weaker the acid, and the more it tends to lie toward reactants. A weak base is any base that does not completely accept protons. In aqueous solution, most bases are considered to be weak bases. A weak base will react with an acid to accept protons, but only partially. Once again, this results in an equilibrium being established. The equilibrium constant for a weak base reaction is given the symbol Kb, or base association constant. Ammonia is an example of a weak base in water solution. The ammonia reacts with water, forming in equilibrium the ammonium ion and the hydroxide ion. A majority of the ammonia stays in the deprotonated form, with only a fraction of it reacting to form NH4+ and OH-. As before, the smaller the value of Kb, the weaker the base is, and the more the reaction tends to lie with reactants. There is an inverse relationship between the strength of any acid and its conjugate base. The stronger an acid is, the weaker its conjugate base will be. Likewise, the stronger a base is, the weaker its conjugate acid will be. The conjugate of any weak species will always itself be a weak species. A weak acid will have a weak base for a conjugate, and vice versa. When considering the conjugate base of a strong acid, we say that it has negligible basicity. It will not accept a proton in water solution. The chloride ion is an example of this, being the conjugate base of the strong acid hydrochloric acid. The chloride ion will not accept a proton in water solution. The conjugate acid of a strong base is said to have negligible acidity. It will not donate a proton in water solution. An example of this is the hydroxide ion. It will not donate a proton to water solution. Notice that it has been mentioned several times that the identity of the solvent is important. The relative strength of an acid or base depends on the solvent in which it is dissolved. Those strong acids and bases that we mentioned earlier are considered strong in aqueous solution, but they may be weak in a different solvent. This is due to a phenomenon known as the leveling effect. Every solvent has a certain acid and base that are the strongest possible acid and base that can exist in that solvent. For water, the strongest possible acid is the hydronium ion. Likewise, the strongest possible base in water is the hydroxide ion. We cannot have any species stronger than those two present in water solution. Any acid that is stronger than hydronium ion will completely level to hydronium ion, since we cannot have a stronger acid in water. Any base that is stronger than hydroxide ion will completely level to hydroxide ion, since we cannot have a stronger base in water. This table contains a number of different acid-base conjugate pairs. It demonstrates the relative strength of several acids and their conjugate bases. If we look on the left-hand side of the table in red, we see the acids. The higher up on the left-hand side, the stronger the acid is. On the right-hand side, the blue species are all bases. The lower down on the right-hand side, the stronger the base is. Note that anything above hydronium ion on the left-hand side is considered a strong acid. These species will completely level in water solution to form their conjugate base. The conjugate bases, if we look across to the right-hand side, are considered to have negligible basicity. Likewise, anything below hydroxide ion on the right-hand side is considered to be a strong base. Their conjugate acids, looking over to the left-hand column, are considered to have negligible acidity. We can use this table to compare the relative strengths of two different acids or two different bases. In this case, we have highlighted hydrofluoric acid, HF, and hydrogen sulfide, H2S. Because hydrofluoric acid lies higher on the table on the left-hand side than H2S, it is considered to be a stronger acid. Consequently, looking in the right-hand column, we see that the conjugate base of hydrofluoric acid, F-, is a weaker base than the conjugate of H2S, or HS-. This is because the HS- lies lower on the right-hand side than F-. When an acid-base reaction occurs, the direction of reaction will always depend on the relative stability of each species in water. The stronger a species is, the less stable it is in water. This doesn't matter if we're talking about an acid or a base. It wants to react to form the more stable, weaker conjugate species. We can use the relative strength of the reacting species to determine whether an equilibrium will tend to lie toward reactants or toward products. Let's begin by considering the reaction of hydrogen sulfide with water. The equilibrium is H2S reacting with water to form HS- plus hydronium ion. Our two acids in this reaction are the hydrogen sulfide on the reactant side and the hydronium ion on the product side. The two bases are water on the reactant side and HS- on the product side. Looking at our table, we see that hydrogen sulfide is a weaker acid than hydronium ion because it lies lower on the table on the left-hand side. Likewise, HS- is a stronger base than water because it too lies lower on the table, but this time on the right-hand side. Now, because hydrogen sulfide is a weaker acid than hydronium ion, the hydrogen sulfide is more stable in water. Also, since the HS- ion is a stronger base than water, the HS- is less stable in water solution. As a result, our more stable species are on the reactant side, and the equilibrium will tend to lie toward reactants. Now let's look at the reaction of acetic acid, CH3COOH, with ammonia, NH3. This reacts to form in equilibrium acetate ion and ammonium ion. For this reaction, the two acids are acetic acid on the reactant side and the ammonium ion on the product side. The two bases are ammonia on the reactant side and the acetate ion on the product side. From the table, we see that NH4+ is lower down on the left-hand side than acetic acid and is therefore weaker. Also, on the right-hand side, NH3 is lower down on the table than the acetate ion and is therefore a stronger base. Because the ammonium ion is a weaker acid than acetic acid, NH4+ is more stable in solution. Also, since ammonia is a stronger base than the acetate ion, the NH3 is less stable. This results in the fact that our two weaker, more stable species, the acetate ion and the ammonium ion, are on the product side, which means that the equilibrium will tend to lie toward products for this reaction. In our next lecture, we will discuss a numerical method for determining the relative strengths of acid or base solutions. Before we can move on to that topic, we need to spend a little more time looking at the amphiprotic nature of water. Since water is amphiprotic, it can act as either an acid or a base, and therefore water can react with itself. This reaction, known as the autoionization of water, has two water molecules reacting to form in equilibrium a hydronium ion and a hydroxide ion. As we see, one water molecule acts as an acid, donating a proton, to the other, which acts as a base. This tells us that even pure water does have a non-zero concentration of both hydronium and hydroxide ions. This equilibrium tends to lie very far toward reactants, however. Despite the fact that the concentrations of hydronium and hydroxide ions in pure water are so small, this reaction is a very important one for establishing our relative scale of strengths. Since we have an equilibrium, we know we can write the equilibrium constant expression. In this particular case, it is just the product of the concentration of hydronium ion and the concentration of hydroxide ion. This is a special equilibrium constant expression, and we call it the ion product constant of water. we give it a special symbol, Kw. Like all equilibrium constants, Kw is temperature dependent. However, since we work primarily at 25 degrees Celsius, the value of Kw at this temperature is 1.00 times 10 to the negative 14. This value will be used to establish what is known as the pH scale in the next lecture. You should memorize this value. Since we know that even pure water has some non-zero concentration of the two ions, are we able to determine what the actual concentrations are? The answer is yes, and we have to use an ice table as in our previous chapter. We begin with our initial concentrations, noting that we don't include the water because it is a pure liquid. We assume that the hydronium and hydroxide ions are both initially 0 molar. Next, we know that we have to react in the forward direction to form the two ions. Each of these will form in the amount plus X. This gives our equilibrium concentration line as having X and X for our two concentrations of the ions. Now we can calculate. Kw is equal to the concentration of hydronium ion times the concentration of hydroxide ion. Substituting in the values, we find that 1.00 times 10 to the negative 14 is equal to X times X. Or in this case, X is equal to the square root of 1 times 10 to the negative 14, which is 1 times 10 to the negative 7. Consequently, our concentrations of hydronium and hydroxide ion in pure water are equal, and they are both equal to 1 times 10 to the negative 7 molar. This now allows us to establish our first quantitative discussion of acidity and basicity. In any solution like pure water that has the hydronium ion concentration equal to the hydroxide ion concentration, this solution is said to be neutral. It is neither acidic nor basic. Any solution in which the hydronium ion concentration is larger than the hydroxide ion concentration is an acidic solution. At 25 degrees Celsius, this means that any acidic solution will have a concentration of hydronium ion greater than 1 times 10 to the negative 7 molar. Because we know that the ion product constant expression of water requires that the product of the two ions is equal to 1 times 10 to the negative 14 molar, then an acidic solution is also one in which the hydroxide ion is less than 1 times 10 to the negative 7 molar. Likewise, any solution in which the hydronium ion is less than the hydroxide ion is considered to be a basic solution. At 25 degrees Celsius, this means that a basic solution will have a hydroxide ion concentration greater than 1 times 10 to the negative 7 molar, and a hydronium ion concentration less than 1 times 10 to the negative 7 molar. It is very important to remember that the concentrations of the hydronium ion and the hydroxide ion are tied together by the value of Kw. This requires that as one value goes up, the other one must go down so that the product stays the same. This product of the two will always equal the value of Kw for the temperature you are working at. Consequently, if we know the value of one concentration, we can immediately calculate the value of the other concentration using the Kw expression. In this final example, we will look at 4 different solutions, and based on the concentrations that are given, we will determine if they are acidic, basic, or neutral at 25 degrees Celsius. Further, we will calculate the concentration of the conjugate species. The first solution has a hydronium ion concentration of 1.25 times 10 to the negative 4 molar. This is larger than 1 times 10 to the minus 7 molar. As a result, this first solution is acidic. To calculate the hydroxide ion concentration, we begin by inverting our Kw expression, so that hydroxide ion concentration is equal to Kw divided by the hydronium ion concentration. We can then substitute our values in 1.00 times 10 to the negative 14 for Kw, and 1.25 times 10 to the negative 4 for our concentration of hydronium ion. The resulting value is 8.00 times 10 to the negative 11 molar, which is our concentration of hydroxide ion for solution 1. In the second solution, the concentration of hydroxide ion is listed to be 0.00235 molar. This is quite a bit larger than 1 times 10 to the negative 7 molar, and so this solution is definitely basic. To calculate the hydronium ion concentration, we once again invert our Kw expression. This time, the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration. We can substitute our values in, 1.00 times 10 to the negative 14 for Kw, and 0.00235 for our hydroxide ion concentration. The resulting hydronium ion concentration is 4.26 times 10 to the negative 12 molar. For solution 3, the hydroxide ion concentration is now 9.52 times 10 to the negative 13. This is less than 1 times 10 to the negative 7 molar, and therefore the solution is acidic. The hydronium ion concentration again is Kw divided by the hydroxide ion concentration, or 1.0 times 10 to the negative 14 divided by 9.52 times 10 to the negative 13. This gives a hydronium ion concentration of 0.0105 molar. And lastly, our fourth solution has a hydronium ion concentration of 1.00 times 10 to the negative 8 molar. This is slightly less than 1 times 10 to the negative 7 molar, and so the solution is basic. The hydroxide ion concentration is found to be Kw divided by the hydronium ion concentration, which is 1.00 times 10 to the negative 14 divided by 1.00 times 10 to the negative 8. This gives a hydroxide ion concentration value of 1.00 times 10 to the negative 6 molar for solution 4. This concludes the lecture on relative strengths of acids and bases. We learned several important ideas in this lecture. First, the relative strengths of acids and bases are determined by the hydronium and hydroxide ion in water solution. Strong acids and bases will completely ionize in water solution. Weak acids and bases do not completely ionize. The extent to which they do is determined by the equilibrium constant, either Ka for the weak acid or Kb for the weak base. The stronger an acid or a base is, the weaker its conjugate form is. The stronger an acid or a base, the less stable it is in solution. It wants to react off to form the weaker, more stable conjugate. Autoionization of water establishes a numerical relationship for acidity and basicity. We will develop this further as the pH scale in the next lecture. And finally, the concentrations of hydronium and hydroxide ion in water solution are tied to one another through the value of Kw.